Okay, so today's topic is on work. And I've been discussing work for the last few minutes in terms of like an everyday life context. If I were to ask you what work means to you in your lives, not in physics, you probably mean, well, work is your job, right? And that's one context we use for the word work. Sometimes work means that like you're doing stuff. Like if someone says, I'm going to go put you to work, it might mean that they're like going to like make you do chores or do a task, okay? That's all true. And that's why I started with this slide right here, because like sometimes we talk about our work week, where on Sunday you're excited it's a day off, and then Monday really sucks because you're like, back to work. And then Wednesday you're halfway through the week. You know, Thursday it's getting better. Friday, yeah, weekend, right? Yeah. And then Saturday you're really excited because you got the day off. Okay, that is not what physics means for work. You get what I'm saying here? So although we use the word work in everyday life, that is not what it means in physics. But you asked me a question a while back, Gus, about, well, what is work? So here's what work is in physics. Work is defined as the transfer of mechanical energy from one object or a system to another. That's really technical. Let's try to like put it in people words. Okay, so let's talk about these words one at a time. What does transfer mean? Yeah, it's like a move, something like a give and take, right? Something has some energy and you give it somewhere else, okay? Mechanical energy is a term that I haven't used a lot yet, so maybe we should discuss it a bit. I'll even write it down here. Mechanical energy is like the sum. Do you guys know the word sum, like in math, the sum, like where you add them together? Okay. Mechanical energy refers to like the sum of all energy that like kind of exists, okay? So like all the energy that exists, whether it's light and heat and sound and noise and movement, okay? Mechanical energy kind of refers to like all of that. Let's talk about these light bulbs for a second. What sort of energy are these light bulbs giving off? Obviously light, but heat and sound, right? I mean, just be quiet for a second and listen to the hum. That's actually the projector, I guess, but does that make sense though? That like you can actually hear something, and like if you put your hand right by these light bulbs, you'd be able to feel the heat, okay? Mechanical energy kind of refers to like all of that, okay? So when I talk about the transfer of mechanical energy, I'm not talking about all of the energy being transferred, but I'm talking about like it's being moved from like one form to another. So like some of the electricity is turning into light, or some of my movement is turning into something else. Does that kind of make sense what mechanical energy is? So it kind of just refers to like all of the energy we have, and we're moving it from one form to another. Here is a classic example, a bat and a ball. A ball is moving, let's say, okay, this is kind of an after picture. So let's say that the ball was moving this way. The type of energy we would use to describe that would be kinetic energy. You guys remember that using that word before? Kinetic energy? Kinetic energy basically refers to anything that is moving. Okay, if something is in moving and in motion, it has kinetic energy. Okay. And let's say that the bat hits the ball back the other way. It's now changed its energy because like it used to be going one way and now it's going the other way. Okay. Well, work is defined as that transfer of energy. Why did the ball start going the opposite direction? It is because of work being done. Okay. Now this is where the word work kind of does relate to everyday life. Is that our door? Someone want to grab that real quick? Thanks. Hello? Hey. What's up, guys? Quick question.
Yeah.
What's up?
Like, what is this really?
So what it's saying here, right, is that you used to have a certain mass and now it's been like depleted. We want to know who reacts the most. So the one that reacts the most is going to have lost the most. Does that make sense? Because it started off here and it's gone down to here. So the one that reacts the most readily, that means like who's the most reactive. Tell me who has like the biggest change.
Oh, okay.
That make sense?
Can I just finish this in the sentence?
Sure, yeah, I'm just going to try to keep teaching my lesson if that's okay. That'll work. Yeah. Okay. Sorry, guys. Where was I? Work. Okay. So work in everyday life is like when you do stuff. You guys with me again? Work is when you do stuff. Okay. The stuff that you do really means that you're transferring some of your energy from one form to another. So ball was going this way, you hit it back that way. Here's another definition for work. Work is done when you apply a force over a distance. Let's say you're hitting this baseball right here. In order to hit the baseball, you have to be quite forceful. You guys know what like force refers to? It's like your punching power in a way, right? Like if I was a boxer and I gave someone like a little light jab, that's not quite as much force as if I went up for big haymaker. You know what I mean? So like force is like the impact you have. So when you do some sort of impact over a distance, that's work. Sure, exactly, right? Sports are a great analogy for doing work because you're putting objects into motion. Okay, that's what this slide here talks about. What is a force? The best definition I've ever heard for force is it's a push or a pull. But like maybe the word you want to use is the word impact, right? Like a punch. That's a force, right? And the harder you punch, the more force you have. In a way, a punch then would be a push, right? But like in theory, you could also pull on objects. Really, one is going forward, one's going backwards. And the idea behind this work is that energy is being transferred, right? There was energy in my fist, and now that energy in my fist has now hit the other person in the face. Okay, that's a bad example. We're boxing, by the way, not fighting. It's boxing. But do you get the concept here? Is that like if you apply a force, it's going to transfer energy. It's going to cause things to move. This is the really key thing here. If things are now moving, we now have forces, and we have energy, and we have work. And they all kind of refer to the same thing, but they're all slightly different. Okay. We've talked about energy before. Work is what causes changes in energy, and work happens because of forces. Can I say this one more time? Hopefully you have an idea in your mind a bit of like some forms of energy. Okay. Work is what changes those forms of energy. Okay. For example, let's say I'm throwing a ball. A ball is moving and I throw it. I've now done work to make it go faster. I've given it more energy. Okay. How did I give it that work? Through applying a force. That's actually what I talk about right here. What is that definition of energy? Okay. You guys hopefully know a few forms of energy. Things like light, heat, sound, radiant energy, nuclear energy, kinetic energy, the energy of motion, solar energy. Thank you. Yeah, right? So those are all examples of energy. What we now have as a better definition of energy, I couldn't give you this definition on day one because we really hadn't discussed work yet. But energy is actually typically defined as an object's or system's ability to do work. If you have the ability to like use some sort of force or do something, that means you have energy. So they're all kind of interrelated in a way. All these words, energy, work, and force. So let's add a new formula to our list. Okay, we have learned 4 physics formulas so far. Let me just rewrite them down again. One of them was if you change a distance over a time, you get yourself a velocity. A second one is that if you have a change in velocity over a change in time, you have an acceleration. And then there's 2 that are very similar. D equals VFT minus 1/2 AT squared, and D equals VIT plus 1/2 AT squared. These are the 4 formulas we've learned so far. Well, this one's number 5. And there is not an easier formula in the world. Here's the formula. If you do some work, that work can change energy. Okay. If you do some work, you can change energies. For example, these light bulbs are doing work. How do the light bulbs run? What sort of energy provides the source to make our lights run? What kind of energy is it? Electricity. Yeah, electrical energy, right? The light bulbs are then going to do work, and they're going to change that energy into many different forms. Light, heat, sound. Mostly light. Does that make sense? So if you ever want to change energy around, it's because you're doing work. So this is literally like the easiest formula in the world. If I tell you that you did 5 units of work, you can change 5 units of energy. Okay. Here's a second formula. Well, then what is work equivalent to? Work is the letter W, and it's actually a capital W, so I'm sorry that this is a small w here, but we actually use capital W for work. Capital W for work. F is force, which is like how much impact, oomph you have. And D, we've already used D before. D stands for distance. So we've now added two new formulas to our list. One is that work is what causes energy to change. And then the second question is, well, how do we even do work in the first place? To do some work, you better apply some force, and you better move something. Okay. Classic example, I want you to move some rocks. Okay. Is it going to be easy for you to lift up rocks? No, they're heavy. So you better apply a force to lift those rocks. But you also need to move the rocks from one side to the other, so you also have to work on a distance. Okay. So here's what I need you guys to know. Work has two different units we can use. The unit we use for force is a capital N. Anybody have any idea what the N stands for? Say it louder. It's called a Newton, yes. We called the unit of force a Newton. Newton, that's Newton. After Sir Isaac Newton. Maybe you've heard the legend about how like an apple fell on his head and he somehow thought of gravity. That didn't actually happen, by the way. That's not a true story. But if you've heard of Newton, Newton did come up with gravity, but it's not because an apple hit him on the head. Yeah, that was a lie. It's just a fun story to tell little kids. Did I just like wreck your childhood here? Well, I mean, he was a scientist. He worked on this for years. He didn't just all of a sudden get hit on a head and go like, hey, gravity. Like, no.
I've been believing that for like 10 years.
I'm sorry to ruin your childhood. So anyways, we named it after Sir Isaac Newton. He was a famous physicist. Not Cam Newton, no. He's a mediocre football player. Okay, he's actually not bad. Taking shots. Well, he's not on the Patriots, so. Okay, I'm getting off topic here. So we use the letter N, Newton, to describe anything that's a force. So that's Newton. I'm sorry, I put the T kind of in the wrong spot there. The other unit I need you guys to know is that when you take a Newton and times it by a meter, which is your unit for distance, that's the unit for work, but NM is kind of awkward, so we use the letter J to describe work. And J is a joule, which we named in honor of James Joule, who we've actually discussed earlier in this course. He did an experiment where he tried to figure out like spinning a rotating motor in a cup of water, how much energy there was by like dropping a weight. You guys recall that topic there? So those are the units we use. Newtons are for force, and joules are for work. However, I want to go back a slide. Remember how work causes energy to change? Work is basically like kind of the same thing as energy. Here's what this means then. Joules is then the unit for both work and energy. So you can use joules for energy or work as your unit. So let's do some practice questions now. Now that I've kind of like discussed these concepts, hopefully by doing some of the math, it'll help like solidify what makes an energy versus a work versus a force. Oh, actually, no, I have more pictures first. You know what? Why don't I skip the pictures and go to the example, and then I'll come back to the pictures. Let's do the math one first. Okay, here's a scenario. You are going to exert a force of 25 newtons, on your textbook. Why are you lifting your textbook? Because you want to put it up on the shelf of your locker. Do you need a lot of force to lift a textbook? I mean, unless it's like a really heavy textbook, you probably don't need to use a lot of force, right? But like the heavier it is, the more force you'd need to use. Is that kind of logical? But since it's just a textbook, we're only going to be using 25 newtons worth of force to lift this thing up. But the other thing we need to know is how far we're lifting it. 1.4 meters. Okay? Because here's the thing. Let's say that you had to lift your textbook a little ways, or you had to move it a really, really far distance. Wouldn't you guys agree that if you move something further, you're using more effort, aren't you? Right? I mean, let's just use a silly example here. I am going to use some force. Oh, here we go. I'm going to use some force, and I'm going to move this chair. Whoa, that was a lot of work I just did there, right? Okay. But like, I moved it like this far, right? But if I moved it further, wouldn't you guys agree I did more work, right? Now, let's talk about that again, though. I was moving a really light chair. Stay with me, guys. That's what I'm going to go to next. Ooh. But let's say I need to move the pool table. The pool table is heavier. Ugh. I might have done just as much work there because I had to push harder, and I didn't actually move it very far. So there's two factors: how much effort you need to use and how far you move it. So the math is actually pretty easy here. Here's your formula. So the formula is that work is equal to force times distance. I'm literally multiplying two numbers here. 25 newtons is going to get multiplied by 1.4 meters, and we're done. Although I do got to point out, make sure you get the little details right, because I know a few of you made mistakes on your quiz because like you didn't round properly or you didn't consider proper significant digits. So 25 times 1.4, my calculator gives me 35. Anybody else get 35? Okay. The last thing we need to know is what unit do we use for force or for work? Or joules is preferred. Newton meters is valid, but we like joules better. Okay. Do we have the right number of digits? Yeah, because this one has 2 digits, this one has 2 digits. I don't even need to round. We're good. That one's easy. So hopefully that one's pretty straightforward. Let's try another one. You do 64.7 joules of work while lifting a heavy object, and you move at a distance of 5.74 meters. Now I want to know how much force you used. So I'm going to write out my formula again. Work is equal to force times distance. But this time around, I know how much work I did. This number right here is 64.7 joules. I don't know how much force I used, and I need to multiply it by a distance of 5.73 meters. Unfortunately, this isn't one of the triangle type questions. But that being said, I really hope that I can help you with this algebra here. To get this force value by itself, all you have to do is divide both sides by 5.73 meters. And if you divide both sides by 5.73 meters, this kind of algebraically cancels, and you have your answer. So your force value is your work divided by your distance. So 64.7 divided by 5.73. Here's what my calculator spits out. Question? You can. You would have to rearrange it, I guess. Like you'd have to make yourself your own triangle, I guess. Yeah, I guess you could say like F equals W over D. Like you could make a triangle if you wanted. Is that what you just said? Yeah. Like you could, I guess. So, what I'd really like to encourage in you guys though is, especially because we're going to get to formulas that look like these ones here, not every formula is going to fit a triangle. So I like to show you it at first, but if you can, try to get away from that triangle because it only works sometimes. I guess you can make it work here. Okay, back to our question here. I got 11.29144852. So, I mean, hopefully you guys are able to divide those two numbers and get that value. We need to round it properly. So let's talk significant digits again. This had 3 digits. This had 3 digits. This number right here, I got to round so it has 3 digits. The first measuring number I got was this 1 right here. I'm going to keep that 1. The next measuring number I got was this 1 right here. I'll keep that 1. The next number I got right here was a 2. That's my 3rd digit. But the number after the 2 is a 9, so we're going to round it up to 3. And newtons is my force value. That is how many newtons we used. Does that make sense? One of the things that some kids like about physics is if they're good at math, all I really need to do is show you a new formula, and you go, oh, okay, well, I can use this new formula. You really just need to know what you're talking about in the formula. So once you wrap your head around what work and force are, then it's just more math. Why don't I go back to the picture slides I skipped for a second now? Because I skipped a couple of pictures. Let's rediscuss now what makes something a force versus a work. Okay, so here's a couple of examples. Let's say that you lift a ball up. You are using an upward force to lift it up. The work you do, though, depends on how far you move it. If you move the ball from here to here, you do some work. But if you moved the ball from here to here, you're doing more work, right? Another way that you could do more work is, what if this wasn't a basketball? What if it was like a cinder block and it's really heavy? Yeah, like the heavier it is, wouldn't you guys agree you would need more force? So that's why you need to have both force and distance. Here's another example of a force. As you turn the corkscrew, you're applying a force to do it. And what it talks about in this picture here is that energy is being transferred. You're using your energy as a human being to apply work to like force this thing into a circular motion. Force it into like torquing a circle. Here's another picture though. I want to talk about this one for a second here. Let's say that this bike rider is going this direction here, but he's coasting. Let's say you're not pedaling. You are actually doing no work. And here's the reason why. Is this person exerting any energy by just sitting there and letting the bike carry them forward? No. They're just being lazy and letting like their momentum carry them forward. And so in order for you to actually be doing work, you have to be applying a force over a distance. Yes, this person is moving a distance, but if they're not actually pedaling, from a physics point of view, they're not actually doing work. Why are they not doing work? Well, yes, they're not using a force, but also this person's not exerting any energy. And energy is also related to work. Let's try another example here. You use 3.4 newtons of force to hold your textbook and carry it 18.3 meters down the hallway under your arm. How much work have you done? Why don't you guys give it a try? You use 3.4 newtons of force to hold your textbook and carry it 18.3 meters down the hallway under your arm. How much work have you done? I certainly don't mean to like belittle anybody who does struggle with this, but like there's only two numbers. You're either multiplying or dividing them. Right? Like there's not a lot of choices here. Right? So the formula is work equals force times distance. Do we need to multiply the numbers or divide them? Multiply them. 3.4 newtons has to multiply by 18.3 meters. 3.4 times 18.3 rounded nicely, because this probably needs to be rounded. I got the answer 62.22. But we need to round it to just the number 62 joules. Is everybody able to get that number? You guys okay on that one? Do stop me if you couldn't multiply those and round it. Yeah. E10 or E1. Yeah, we could do that too. Yeah. Okay, I need to actually point something out here. I lied to you on this example here. I made it seem like it was really easy. There's actually a trick question on this one right here. The answer is actually 0 joules. It's actually a trick question. Let me try to explain why now. Do you think you know why? Okay, let's draw a picture here. Here's a person. This person is holding a book. When the person is holding the book, they're actually holding the book up. Because doesn't the book naturally want to fall? Okay. But now when the person is walking this way. Is the force that they are using in the same direction as the distance they're traveling? The answer is no. In order for you to do work, you have to push an object, and it has to keep going that same direction. So this is kind of a trick question, but like technically you didn't do any work. Were you applying a force? Yeah, you were holding a book up, but then you walked forwards. Does that make sense? And since it wasn't in the same direction, the word I want to talk about here is something we've already mentioned before. It's something called a vector. Direction matters. They have to be going in the same direction for this to work. Yeah. Okay, so I would say that you lifting it up, when you lifted it up, you did work. And now that it's sitting there, now you're not doing work anymore. But you have to be, it has to happen over, keep moving over a distance. Does that make sense? So like you did the work against a gravity to get the book from here to here, but if it's not moving anymore, it's not, there's no work being done. from a physics point of view. And this is where people sometimes struggle because you're like, but I should get credit. I'm holding this up. But like from a physics point of view, it has to be moving while you're applying a force. Does that kind of clear things up? So because your force is keeping it up, but the distance is going this way, I can give you credit for moving the book from here to here. Does that make sense? When you move the book from the floor up to here, I can give you credit for work. But as soon as you move it that way, it's the wrong direction because the vector part is wrong. Sneaky, hey? Okay. Let's try another example here. This is another trick question. Let's say that you push with 85.6 newtons against an immovable object. So like hypothetically, it's wintertime, your car gets stuck in the snowbank, you get out and you try to push it, and it does not move. Did you do any work? Technically, from a physics point of view, no. You might be sweating because you're like straining with all your might trying to push that stupid car out of the snowbank. I'm going to tell you, you are using a force. Okay? I'm not going to, like, you get credit for using force, but if it does not actually move, you're not actually doing work according to a physics point of view. Okay? So the answer to this one, just like the previous question, is you actually did no work. Does that make sense? Okay. Oh, let's try another one here. A championship weightlifter is going to use 6,000 joules of energy to lift this barbell 180 centimeters above his head. Let's figure out how much force he would need. This is probably a pretty heavy barbell, right? Now, what I want to point out on this example here is when you use the formula work equals force times distance, we have a little bit of an issue here. I'm going to throw the number 6,000.0 right here for work, but I'm not going to throw the number 180 right here. Does anybody know why it's wrong for me to throw the number 180 right there? And this is measured in centimeters. Okay. So we have to be careful on this sometimes, is that we have to have the units be proper. Now, it really helps then if you know what a centimeter is. A centimeter, if you have that like table printed off in your data booklet somewhere, a centimeter is a times 10 to the minus 2. Is that a question? Or are you just going to tell me what it was? Okay. A centimeter is a 10 to the minus 2, or an E minus 2. In our notes one day, I gave you like a big chart that told you everything from like a giga and a tera and an exo, all the way down to like the littlest ones. On your quiz, not that I want to give it away if you haven't finished, but one of the questions asked you to convert to megaliters, and some of you I think got mega and milli mixed up. So like, make sure you know your prefixes. Long story short, I need to make this 180 times 10 to the minus 2 meters. I need to make this number smaller. Now, if you'd like to, you could even do this. You could make it 6,000 equals F times 1.80. You could move the decimal place back twice if you want, but like, you have to convert this number and not divide by 180. So you're actually dividing by 1.80 when you do this. And let's get an answer. 6,000 divided by 1.80 meters. Yeah, I get 3.3 repeating number. Okay, so let's talk sig digs here. This number right here at the top here has 5 significant digits. And the reason why it has 5 significant digits is that I actually did record this 0 right here. If I didn't record this 0, I actually wouldn't really be sure how many significant digits it has. So, but this one for sure has 5. This number right here, however, has been poorly written. I don't know how many significant digits 180 has. It could be 3. It could be 2. And I'm not really sure how many it has. So I will not give you a question like this where I'm ambiguous here, because that's poorly done. So why don't we change this, and why don't we say that it was like 1.80 E2 centimeters? Let's just like say that it has 3 sig digs. Let's write it differently. So if it has 3 significant digits, then we need to like round this number to 3 significant digits and make it 3.33 times 10 to the 3, I think it was, newtons. We have to move the decimal place over 3 times to make it work. That's how much force you needed. If you want to, you could write it as 3.33E3. That helps if you like that method. I really don't care. So what I wanted you to learn from this question here then was be careful about units. If it's not in meters, you got to convert. And if you're not good at converting, I can help. Okay? Identify what it is that you need work on, and I can help fix it. Okay, I think this is my last example. A crane is going to use 6.0 times 10 to the 2 joules of energy to move a container an average force of 260 newtons. This is another good example of talking about significant digits. The number 6.0 times 10 to the 2 is really like 600, right? Because if you move the decimal place over 2 times, you get 600. But why do I not like writing the number 600? I don't know what it was rounded to. Is this a number rounded to the nearest ones? Was this a number rounded to the nearest tens or hundreds? Now I know. By writing it with 2 digits, this was a number that was rounded to the nearest tens. So anyways, it's 600 joules, but I only get 2 sig digs. The force being used was 260 newtons. Now, this number here was ambiguous. I don't know whether it had 2 or 3 sig digs. It doesn't matter though, does it? Because if this one had 2 or 3 sig digs, but that one had 2, I have my answer. I'm rounding it to 2 sig digs. So, use our formula then. Force times distance is equal to work. I'm going to write it backwards even, just because. My work, though, it doesn't tell me how much work I did. But you know what it said, though? It said I had energy. Isn't work the same as energy, though? Don't we have a formula from way back here that says that work is the change in energy? Right? So if it tells me how much energy I used, I actually forgot to mention that on this last question here. Here I did the same thing. See how it said I had energy right here? If I didn't point this out on the last example and you figured it out on your own, but energy is work. So same sort of thing here. This energy value is your work. And your force is the 260. This is in newtons, so it's good to go. So divide both sides by 260. And I'll get my distance. 600 divided by 240. No, 600 divided by 260. Here's what my calculator spits out. I got 2.307, and it just kind of keeps going like that for forever. This is why rounding is so important. We only get to keep a certain amount of digits. We have to round at some point. If you're wondering, Chris, why are there these stupid significant digit rules? It's for this example right here. The question was, well, I got to round. So to be consistent, since this had 2 digits and this had maybe 2 or 3, this number here should only have 2 digits as well. So it was 2.3 meters. That's how far this crane lifted this guy up. Actually, that seems logical, doesn't it? Doesn't 2.3 meters kind of make sense for this guy lifting it up? Let's say that this little motorized device here then takes this container and then it moves it that way. Does it get credit for doing work? Nope, only for the lifting up portion. I know it seems kind of weird, okay? But from a physics point of view, an object has to move and force has to be applied for it to be considered work in a physics sense of the word. Okay. There's still force being applied. There is still a force keeping this thing going upwards. Okay. So the force is still applying, but it's not considered technically work. Okay, that's my lesson. So let me do a quick recap here. We've now added 2 new formulas to our list. Hopefully you'll agree that the formulas are not that hard, hopefully. Like literally one of them is that W is E. If you have work, you have energy. Okay. Why? Well, energy lets you do work. What is work then? Work is where you move an object, so therefore there's a distance. And in order to move the object, you applied some sort of push or pull, like some sort of oomph. Got it moving. That's your force. Okay. So it's not a triangle formula directly, but hopefully you know how to use it. It's not one of the more, it's not as hard as these formulas back here. Like, where are them? These 2 formulas right here, these ones are way more challenging to work with than like work is force times distance. So, Okay, questions, comments, concerns, conundrums, curiosities, complaints, criticisms, queries. I'm out of cool words. Okay. Okay, so here's what I want to do. We still have a little bit of time left today. Let me give you 3 things that you can spend your time doing now. Option 1, you can work on that assignment. There's 1 assignment for the whole unit, that's it. You can't do all of it, but you can do a little bit more now. You can work on that. That's option 1. Option 2, we did an activity the other day where we raced Hot Wheels down the hallways. Finish that up as soon as you can. Okay. Option 3, this is what I think is your best option. We wrote a quiz yesterday. And like I kind of was on my soapbox kind of preaching to at the beginning of class, if you want to do well, and I like to hope that you guys are here because you want to do well, I can help with that. I think the key to that is self-reflection and seeking feedback. Go over your quiz from yesterday or finish your quiz from yesterday. Figure out whatever it is that you made mistakes on and have me try to help you. Okay? If you don't ever improve on your mistakes, you don't get better. Okay? I think that's the single most important thing you can do. And it doesn't necessarily help your mark because, yeah, your mark is your mark from your quiz. Okay? But please don't associate your self-value and your worth by what like a number on a sheet of paper says. If you got 17 out of 25 or 2 out of 25 or 24 out of 25, guys, it doesn't really matter yet because we're only in the dress rehearsal stage right now. This isn't the playoff game yet. Does that make sense? For my analogy, right? We're learning still. So I don't care if you make mistakes, but let me help you improve on them. Okay? So please use that little bar thing right there to rank your confidence because I think it helps. In hindsight, then you can look back and figure out what is it that I was not sure of so I can ask for help. Okay, that's all I've got. So I'll shut up now. You guys are welcome to go somewhere else if you want, by the way. You don't have to stay here if you don't want.